when we have a coil, the coil is just simply a long stretch of wire. And we learned in the resistivity lab that what happens to resistance as the wire gets longer and longer and longer, the resistance goes up. And so although a coil is often measured in terms of its inductive properties, and we'll look at inductance later on in the semester, and by the way, inductance is measured in henries. So if the instructions say, look at the 8.2 millihenry inductor, that's just a coil that has an inductive property of 8.2 millihenries. Today, we're just simply looking at the resistive value of the length of wire. So if it looks like just a long length of wire and therefore has resistance in this case, what should the plot look like? Voltage versus current, we should get some straight line whose slope is the resistance of the coil. And later on in the semester, we're going to use this coil in a couple different experiments. And you need to remember that that coil acts as two things. One is a coil with inductive properties, but it also acts like a resistor. Okay? And so you have to remember that it is an extra resistor in the circuit because it's a long stretch of wire. Now, coils are used in many different situations. We will drop a magnet through a coil and see that we can actually induce a current. And so we know that coils are used in a spinning fashion near magnets, or spinning the magnets near a coil, either way, to generate electricity. And in fact, the electricity that's coming through the wall and is powering these computers comes from some sort of generator that's spinning because, say, there's water hitting a turbine or there's steam going through, spinning a turbine. In your car, you have a generator. It's called an alternator. And that alternator is spinning, and there's coil and magnets in there, and it's inducing current and therefore charging your battery. Coils are also used in transformers, okay, to go from one voltage value to another voltage value. You've got lots of transformers at home, right? You plug in a device and it charges your cell phone. And I think those often also have a rectifier in them because you're not only stepping the voltage down, but you're also changing from AC to DC. Coils are also used in, say high-end equipment. You'll see that it protects from a voltage spike, and that's part of the inductive property. We'll look at that later in the semester with the RLC lab. R, resistor, L, inductor, and C, capacitor. And we'll see that at high frequencies, the inductor becomes very active in inhibiting. And so if you have a spike to an electrical component, say a really nice amplifier in your stereo system, the coil is going to protect from that spike. You can test for that by just turning off your stereo, and if the light just goes out like that, it doesn't have protection. But if you turn off your radio or your amplifier and the LED light on the power just goes like this, okay, just goes just out slowly, well, that's a coil that's in there, and it's actually protecting the circuit. Now, what is the job of a capacitor? A capacitor symbol looks like this. It's two plates separated with a dielectric, or in other words, it's two plates separated with an insulator, an electrical insulator that does not allow current flow. Instead, it allows charge buildup. Okay, so we can create a temporary battery with this capacitor. We can put charges over here, and opposite charges will collect on this side, making this look like a positive-negative potential difference, just like a battery. A capacitor has this principle that when you're charging it, it's really easy at the beginning because you're putting individual charges on there and they just spread out, and you put the next one on, and that's pretty easy. But the more you put charges on there, the more work you have to do to put the next one on. And so capacitors are also used with what's known as a time constant. A capacitor you might have in, say, your car for the blinker. So you have two blinker lights, front and back, and then you turn on the blinker and it's blinking, and it's a capacitor that's in charge of that timing. So yeah, capacitors are used in many, many different situations. Not sure how keyboards are made today, but in the past, electronic keyboards were made with a capacitor. And so when you push down on the key, it actually sent a charge through to say that, that key has been pressed. So let's think about the consequences of this discussion upon the plot of voltage versus current for a capacitor. Now, what did we say about the capacitor? It was two plates that charge up, and they're separated with a dielectric. They're separated with an insulator that does not allow what? Remember the prepositions. Voltage is across, but what is current? Current is through. And the capacitor is designed to not allow current to go through. But how did we define resistance? It's the ratio of voltage to current. And if in the current, in the denominator, we have 0, then what do we have for resistance? Or can we even speak to the resistance? What happens when you take a number, say voltage, and divide by 0, because there is no current? It's not infinite, is it? It's rather undefined. So we'd have to say that the capacitor, unlike all these other components, the capacitor does not obey Ohm's law. The capacitor disobeys Ohm's law because, or actually we should just say it ignores it completely. If you don't have any current through, then you can't even talk about Ohm's law. Now, practically speaking, capacitors have some leaking, and so there is some current, and we could say that there is resistance, and it's really, 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 really high. Okay? So what should this plot look like when we look at voltage versus current? Oh, by the way, here's an image of the dielectric and how charges are building up here, positive and negative on this side, and the dielectric inside is reverse charged. And this acts like a temporary battery that can discharge, say, into a light bulb and light up the light bulb for a short time. And then all the charges have dissipated and the light bulb dies. Voltage versus current. What did we say about the current? How much current is going through, measurable for us today? How much current is going through the capacitor? None. So this plot should look like this, just a vertical line. But I think you'll find when you take the data, you actually see something like this. Okay, and that's not to make you think that, oh, we're suddenly activating Ohm's law for the capacitor. No, this wiggle in the acceleration is this wiggle in the current is simply a factor of the uncertainty in the measurement. The interface cannot know the current exactly. It's plus or minus so much because of the uncertainty. It's in the milliamp range. And so we're going to see, if you zoom in, you'll see some data that's wiggling. What is the slope of a vertical line? It is undefined. Okay, and so we'd have to say Ohm's law does not apply to this situation because there is no current through the capacitor, and therefore the resistance is undefined. Now on the same page, you're analyzing both the coil and the capacitors, and so you just want to note some things about those two situations, about the coil and what the resistance is, and then make a statement about the capacitors and Ohm's law and whether or not you can say anything about the resistance for the capacitor.